In lesson 3, we're going to start to look at some of the properties of vectors. So as we mentioned, vectors have a magnitude and a direction. So the first property that we can look at is that vectors are considered equal if they have the same magnitude and the same direction. The location of the vector does not matter as long as they're going in the same direction. So generally, to be going in the same direction, they would need to be parallel and they would need to be the same length. So here we have 3 vectors labeled P, Q, and R. So we can see that they're all the same magnitude and they're all going in the same direction. So we could say that P equals Q equals R, or we could use the start and end point vector AB is equal to vector CD, which is equal to vector EF. Vectors can also be opposites. So if they are opposite, they would have the same length or magnitude, but they would be opposite in direction. So here we see vector V or vector AB is the same length, but opposite in direction to B to A. So A to B is considered the opposite of B to A, or vice versa. So we can write this in a couple at the vectors here. If I go from A to B, the opposite would be going from B to A. Different ways. We could say that AB, the opposite of AB is negative AB, or we could reverse the direction. If you look, so I could say the opposite of AB is negative AB, or I could say it's the same as going from B to A. A unit vector specifies direction and it has a magnitude equal to 1. So we will look at unit vectors in greater detail in units 3 and 4. But just as an introduction, if you think of it like a unit price, so let's say you're going to the grocery store and you buy a package of juice boxes and maybe there's 8 in a package, you could calculate the unit price by taking the total price and dividing by how many boxes are in the package. So let's say you had a package of juice boxes for $2.99 and there are 8 boxes in the package. You could divide the total price by the number of juice boxes and figure out the unit price, which is about 38 cents. So a unit vector is similar. You can find the unit vector by dividing a vector by its magnitude. You'll notice that the symbol for a unit vector is V hat or V cap. So it has that little cap symbol on it, which is different than a vector, which is an arrow. So if you see that little cap or hat on the V, that means that we are referring to the unit vector. Just rearranging this equation here. So any vector can be expressed as a product of its magnitude and its unit vector. So if a unit vector equals a vector divided by its magnitude, and we isolated for V, so if we wanted to get this, it would be the same as multiplying a unit vector by its magnitude. So here we have sort of a diagram or visual of what a unit vector is. So let's say we had this vector V. We can see that it's 1, 2, 3, 4, 5 units long. A unit vector would be 1 unit. So this vector is consisting of 5 unit vectors. Or we could say vector V is 5 of these unit vectors. So the magnitude is 5, and it'd be 5 times this unit vector. So this vector is made up of 5 of these individual unit vectors. So as I said, we will look at this in greater detail in the next units, but this is more of an introduction of the properties. We'll also look at scalar multiplication. So a scalar multiplication makes a new vector by changing its magnitude. So we're not changing the direction, we're just either making it longer or shorter. So we can scale it up or scale it down depending on a factor k. So if k is bigger, it's going to make it longer. If it's smaller than 1, it'll make it shorter. And we can also change the direction in the opposite direction if it's indicated that it's negative. So for example, let's say we had vector v and vector w. So I'm just going to draw them on this grid here. So I'll just make up some numbers here. Let's make vector v over 4 up 3. So I'm going to make this vector v, just for argument's sake. And I'll make w, we'll just put w up here. So w, let's make it 4 units long. So I'm just making up some numbers here. So let's say I wanted to do a new vector a, and I wanted it to be 3 times vector v. So vector v, if I go from start to end, I went right 4 and up 3. So in order to make vector a, I'm going to have to do that 3 times. So I could pick any spot. I'll pick the same spot. So I'm going to go right 4 up 3. There's 1. I'm going to go right 4 up 3. There's another. And then I would go right 4. I'll just have to extend this. And up 3. There's another. So from start to end, this vector from start to end would be 3 times vector v. So it's going in the same direction as v. It's just 3 times as long as v. If I wanted to do a vector that was 1/2 of w and it's negative, so it has to go in the opposite direction, well, w is 4 units long, so half of that would be 2, and it would have to go in the opposite direction. Just let me label this as vector a. So vector b, I could pick any point to start, doesn't matter where. It has to go in the opposite direction of w and half as long. So there would be an example of vector b. So vector b is half the magnitude of w going in the opposite direction. And then vector c would have to be -4 times w. So again, it would have to be 4 times as long as w going in the opposite direction. So if this was 4, it would have to be 16 long. I'm going to run out of room on that. And it would have to go in the opposite direction. So it would have to go this way, and it would have to go 16 units. So I'd have to measure out 4 times. I'm not going to do that because I don't have a big enough grid, but I would have to go 16 units long. Parallel vectors have the same or opposite direction. They don't have to be the same length, but they have to go either in the same or opposite direction. So 2 vectors are parallel only if they are scalar multiples of each other. So let's look at a couple of examples. So here I have figure A, B, C, D, E, F. It is a regular hexagon, meaning that all the sides are the same length. So A to B is the same length as B to C, is the same length as C to D, and so on. So I want to write an example of vectors which are equal. So remember, if they're equal, they have to go in the same direction, and they have to be equal in length or magnitude. There's lots of options here. There's more than one answer. So let's say we decided to choose AB. If I start at A and go to B, a vector that would be equal to that would be E to D. E to D is going in the same direction as A to B, and it is the same length. Or let's say I went from C to D. Starting at C and going to D, a vector that is equal would be A to F. It's going in the same direction, and it is the same length. So there's lots of different examples of equal vectors. Opposite vectors have to be equal in magnitude, but opposite in direction. So let's just pick a vector. I'm going to pick B to C. So if I start at B and go to C, it has the same magnitude as F to E, but we want it in opposite direction. So I would say E to F is opposite to, I'm not going to write that they're equal because they're not, opposite to E to F. Okay, so B to C is opposite to E to F, or I could say B to C is equal, if I wanted to actually write a true statement, I could say B to C is equal to the opposite of E to F. So the opposite of E to F would be F to E. So B to C is equal to F to E, or B to C is equal to the opposite of E to F. Parallel but different magnitudes. So they have to be parallel lines but different lengths. So I would say maybe D to C. D to C is parallel to E to B, but they're not the same length. So I would say D to C and E to B. So E to B is parallel to D to C, but it's longer. Different in magnitude and direction. Lots of examples here. I might say F to B and maybe D to C, right? F to B and D to C, they're not parallel and they're different lengths. Okay, so you can just pick, there's lots of different answers for these examples. There's not just one answer. We have lots of different opportunities to write equal vectors in here, opposite, and so on. Here's another example where we have a line and we have points A, B, C, D, E, F, and G. They are equally spaced along the line, so that means the space in between them is the same. And we want to name a vector which is equal to the following. So we want to name a vector that is 3 times as long as B to D. So if I look at B to D is here. B to D is 2 units long and it's going to the right. So if I'm talking about magnitude, I want a vector that is 2 units long and I want it to be 3 times that. So this vector I'm choosing has to be 6 units long and it has to be going to the right, which is the same direction as B to D. So my only option is, because I'm limited by the length, my option would be, let's say we start at A, we're going to go 6 units to the right. So 1, 2, 3, 4, 5, 6 would take me all the way to G. So in that case, I have to start at A because I have to go 6 units and I'm limited by space here. So A to G is 3 times as long as B to D and it's going in the same direction. All right, 1/4 of E to A. So E to A is from here to here. So E to A is 4 units long and it's going to the left. So first we'll talk about magnitude. So E to A is 4 units. So 1/4 of 4 units is 1 unit. So I have to pick a vector that is 1 unit long and it's going to go to the left because E to A goes to the left. So I have lots of options here. I can pick any point. I could pick E to D, or I could pick D to C, or I could pick C to B. As long as that vector was 1 unit long and went in the direction to the left. So lots of different answers for that one. I want a vector that is 5 over 2 in length in terms of D to F. So let's look at D to F. So D to F is from here to here. It's going to the right. It's 2 units long. So if we talk about magnitude, we want a vector that is 5 over 2 times 2 units. So it has to be 5 units long. And it has to go to the right. Okay, I'm just going to put direction here. So B to D went to the right. And E to A went to the left. So I have to pick a vector that is 5 units long and is going to go in the direction to the right. So if I started at A and I went 5 units to the right, that would take me to F, or I could start at B and go to G. So there's really only 2 options for that one because, again, I'm limited by the length of this line. So starting at A, 5 units to the right would take me to F, or starting at B, 5 units to the right would take me to G. Negative 2/3 G to D. So G to D is from here to here. It's 1, 2, 3 units. So we want to go in the opposite direction and we want to do 2/3 of 3 units. So the vector I want has to be 2 units long in the opposite direction of G to D. So G to D goes to the left, so the vector I want needs to go to the right, and it has to be 2 units long. So again, there's more than one option. If I start at A, 2 units to the right would be to C. If I started at B, 2 units to the right would go to D, and so on. I could go from C to E, D to F, or E to G. And then finally, the opposite of twice A to D. So if I look at A to D is 1, 2, 3 units long. So the vector I want has to be 6 units long, and it has to go in the opposite direction of A to D, so it has to go left. So it's really only option because the line is 6 units long, so if I started at G, I would go to A. So G to A is 6 units long, and it's going in the opposite direction of A to D.